The show starts in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
So good evening everyone. It gives me immense pleasure to welcome you all to the second Tech Talk of IEEE Aerospace and Electronic Systems Society on the topic Solving the Cosmic Secrets. With us, we have our distinguished speaker, Dr. Dhrubojyoti Sengupta. Thank you so much for joining us today. And now I would like our advisor, Sir Dr. Jayapanda, to welcome Sir.
Oh my goodness, this conflict. Good evening, Dr. Sengupta. So I'm Dr. Jyotiranjan Panda, is a faculty in School of Electronics Engineering, also advisor IEEE Aerospace Electronic System Society Student Branch Chapter, School of Electronics Engineering, KIIT Dimtube University. So here in India, it's evening, 6:40 p.m. Actually, it's might be in Paris. It is a post-launch session. Might be it is good afternoon. Good afternoon in Paris actually. So you are in Paris. So welcome, and we are grateful to you, sir, for your accepting our invitation to have a technical talk. So it gives me immense pleasure to extend a very warm welcome to all of you to this special invite technical talk organized by the IEEE Aerospace Electronic System Society Student Branch Chapter of School of Electronics Engineering, KIIT Dimtube University, Bhubaneswar. This evening session is indeed a special one, as we are greatly honored to host Dr. Dhrubojyoti Sengupta, postdoctoral researcher at CNRS, French National Center for Scientific Research, and CA, Paris-Saclay, Alternative Energies and Atomic Energy Commission in Paris, France. He specializes in high-energy astrophysics and X-ray studies of active galactic nuclei, investigating how energetic processes around supermassive black holes influence galaxy evolution. Currently, he is extending his work to low-mass dwarf galaxies to uncover how black hole growth begins in the smallest galactic systems of the early universe. On behalf of IEEE AESS SBC KIIT Dimtube University, I would like to extend our heartfelt gratitude to Dr. Sengupta for kindly accepting our invitation despite his busy schedule. We are certain that today's lecture will not only broaden our technical and theoretical understanding, but also ignite curiosity and inspire many young minds to explore the future of space and astronomy. I would also like to thank our faculty, IEEE student members, and all participants for joining us this evening. Let us make this season a memorable one by engaging actively and learning from this distinguished discussion. With that, let us begin today's session. Please join me in warmly welcoming Dr. Sengupta. So welcoming once again Dr. Sengupta. So now the stage is yours. The podium is yours. You can start your technical talk. Thank you. Thank you, sir.
Thank you. Hello, everyone. I will just try to fit the presentation. So give me a few seconds.
Okay. And the audience. The voice comes with.
Okay, I hope you can see my slide in the full screen.
Yes, sir.
Okay, sure. First of all, thank you so much for this kind and warm introduction, and also for this welcoming introduction on me. I'm quite honored also to present, to give a talk like this. But just to the general audience and also to Rajdeep sir and any faculty there, you can just call me by my name. My name is Dhrubojyoti Sengupta, or in short, Dhrubo. You don't need to call, I mean, especially to the students, don't need to call me sir or anything. I'm not in that. You can just call me Dhrubo or Dhrubo Da, as we call in Bangla, our brothers, elder brothers. And so this talk, when Priyadarshini first contacted me, I had to think about a bit on this kind of talk, because most of the talks that I have given till now was to specialist people who works on astrophysics and cosmology. So to give a talk to general audience, I had to go through my basics a bit more, and try to make the talk on the basis of how common people or general people might think. And then obviously I will bring some stuff which is a bit more technical. So the whole journey of cosmology and astrophysics started with asking questions. So it's just curiosity, what is in the space, what is in the sky, and it was there since generations, since our species arrived, I would say. But let's start with this one very trivial question, which I think most of you might know, or most of you might have thought of, but I know that not most actually, probably very few have thought of, because most of the people actually took it for granted that our night sky will be dark. The question is, why is our night sky so dark? Because this is what we see, that you see in this picture, our night sky, where it's absolutely dark with some sparkling points that are either stars or galaxies, and obviously we can also see the moon, our satellite. But why won't we see the sky like this, like extremely bright, full of light? This question was actually baffled astronomers since centuries. I mean, this is actually called Olbers paradox, and Hendrik Olbers was the one who has popularized it. But even a few hundred years ago, people were also questioning this thing. And the reason this question arrives, even though we take it for like a very normal thing that night sky will be dark, but the cosmologists or astronomers actually thought it very interesting and very puzzling, because at that time, even 200 or 300 years ago, we used to, even more than 100 years ago also, we used to think that universe is infinite, which is still probably a bit true, because it's a huge universe. The size of the universe is huge. So it's comparatively, it's you can say that it's infinite. So it extends in all directions, it extends infinitely in all directions. And number two is the stars and galaxies in the universe. That what we have found since all our observations of the sky, that it's almost distributed evenly and uniformly all over the sky. So there are trillions of trillions, not 100 or 1,000 or million, but trillions and trillions of stars that are evenly distributed throughout our sky. And we also know that universe, we also used to think 100 years ago that universe is static. So static universe means that universe had no beginning and no end. So universe was always like this. There were like trillions and trillions of stars. So why didn't the starlight come to our observers, our eye that is on our planet, and we would see something like this, like the very bright sky? So with this condition, it was baffling. So some people may ask that, okay, there are many stars, but the more distant stars are very much fainter, because as things go farther, the luminosity gets low, the intensity gets low. That's true, But if you consider a homogeneous distribution, a uniform distribution of stars and galaxies all over the universe, then we can see that as we go further with this inverse square law of intensity, because intensity diminishes 1 by r square, but as we go further in each block, we see more number of stars also. So the collective effect actually gets cancels out. So we should at least see a huge amount of light whenever we look at the sky like this, eventually at certain point, but we don't see that. The reason is because the problem was in our assumptions. So what we actually see, what we actually understand that universe should be infinite is wrong. Our universe has a finite age, so it had a beginning. Of course, will there be an end, and whatever that would be is still a debatable thing, but universe had a beginning. And the speed of light from Einstein's special theory of relativity, what we found was finite. So with a finite speed and a finite age, we can only see those lights that have managed to reach our eye. So there are trillions and trillions of galaxies and stars whose light we haven't got to see yet. So the question comes, why? Because universe is also not static. Universe is expanding. So even if the light emitted from that galaxy at certain point, the expansion of the universe has taken place so fast that the light didn't have the chance or time to reach towards us. So there is a huge, vast space that we haven't even get to see yet. So the thing that's take away from here is whenever you look into the night sky, is don't just consider from now on after this talk that it's just a dark sky. Consider that you are witnessing the expansion of the universe direct hand, and that's why you are watching a dark sky. So we can go further on that if anyone have more questions after the talk, but I want to proceed on this topic of how we understand that universe was expanding. So the thing was already in the discussion since early 19th century when Einstein published his general theory of relativity paper in 1915. So after that, a legendary astronomer Friedman calculated from the general theory of relativity equation that our universe cannot be static, it should be expanding. Einstein was not very sure of that. Einstein used to believe in a static universe, that no ending, no beginning, it is always as it is. But his own equation was giving that universe should expand. So he was, there is a bit more theory on that, but let's not go in on that. But Friedman, when calculated and showed that we have an expanding universe following Einstein's equation, people started watching the sky and tried to prove this theory or disprove this theory. So Hubble was one of these another legendary astronomers who observed galaxies far, far away. So we live in Milky Way, which is our galaxy, but there are trillions of galaxies, as I said, in all over the universe. So he was looking on all the galaxies, and mostly the galaxies which are very much far away, and he find that the galaxies are moving actually away from us. And they are moving away from us with calculating some Doppler redshift, Doppler velocity. They see that it's redshifted in the Doppler electromagnetic spectrum. So this redshift term it might seem technical, but this is when we say that when something is in the electromagnetic Doppler effect, when something is going away from us, that is redshifted. When something is coming towards us, it's blue shifted. So what he found was all the galaxies are actually redshifted. So it's going away from us. And also he found that more distant the galaxy, it's faster it is receding from us. So you can see this original diagram from Hubble's observation where y-axis is velocity and x is distance. So as we go, we go farther in the away from our galaxy, we see the velocity of receding actually increases, and it increases like a linear equation, which Hubble actually calculated, which is this V is equal to H naught D, where H naught is the proportionality constant coming from the linear fitting, and this H naught is actually called Hubble's constant. The exact value of Hubble's constant is still in a matter of debate, but it is around 70 units. So, but still there are many observations. So this is a very interesting thing of study. So if you are interested to study Hubble's constant or Hubble's law expansion of the universe, you can take a note of this. So what this actually means is, as everything is receding from us, everything, every direction and almost uniformly in a linear pattern, does this mean that we are the center of the universe? The answer is no. That would be a very, very special case, that our Milky Way is the center of this universe. So following the cosmological principle, which is that universe is homogeneous and isotropic at all large distance, we assume that any observer sitting any galaxy, not our Milky Way, if there is another intelligent being in any other galaxies and they even see the universe, they will see the same effect, that all the galaxies are going far and far away from each other. So from this, we have concluded that this is an expanding universe, because if everything going is far away from us, that means an expansion. Imagine you are inside a balloon, and the balloon, you are just giving air to the balloon and it is expanding. So if you are inside the balloon, you will always see that the walls are going farther. So it is just that effect. So let's come, what is making this space go farther? We know that the galaxies are getting farther. So how we deal it is we try to think what happened before. So what happened like millions or billions of years ago? If it is getting farther now, it was probably closer at certain time. So if we go back in time, eventually we will reach a time where we will be much close to each other, and eventually the volume would be very small, but the total mass of matter would remain same. So the density would be very high, because mass by volume. And if the density of the universe was high at that single point, if we put all the universe expansion to one single point, then that point, that instance in space and time is called Big Bang. Just keep in mind that Big Bang is not an explosion. I mean, it's not a bomb. It's an expansion of space. And in general, it's just expansion of space-time metric, but let's call it space for the sake of this talk. And what we found is in this diagram, you see that if this is the point that the expansion of Big Bang happened, gradually with series of cosmological epochs, like stages of our universe, we have come to this point. So this is actually the plot, and we actually also get to calculate the age of the universe, that is around 13.7 billion years, or 1,370 crore years. So this is the age of the universe, means that Big Bang happened 13.7 billion years ago. So if we go to the chronology of the universe, how universe actually formed and started, just to give us a short recap. So from the point this Big Bang took place, we call it t equal to 0, the time 0. So from time 0 to time 10 to the power 43 seconds, universe had huge amount of temperature that we don't know of. And it was very, very small, infinitely dense. And in that part, it's very mysterious how the universe has worked. So even though we have developed so many stuffs, there are still a lot of things to do to understand what exactly happened between 0 and 10 to the power minus 43 seconds. Now this 10 to the power minus 43 seconds might sound a very small number, but in early universe cosmology, this is a huge number, which you will see in some next slides. So why there is, I mean, one of the most peculiar thing in that part, which is still a mystery, is because of the forces. So this is something you might all know, but I am still just giving a repetition that all our interactions or forces in the universe can be classified into 4 types. One is gravity, then is a strong nuclear reaction, weak nuclear reaction, and electromagnetic force. any interaction or any force you see in the universe, or even in close to you, in close to your vicinity, in your, when you walk, when you ride, when you go in an aeroplane, all the force are within either electromagnetic force or gravity. Strong nuclear and weak nuclear force takes place inside an atom. So we can classify it into 4 types. So, but the beauty is we can classify them. The 4 forces are different. We cannot just say gravity is the same kind of force as electromagnetic force. Even though there are some similarities in the formulas, we cannot just say they are exactly equal, because the nature is very different. One is driven by mass, another is driven by charge. Same goes with the strong and the weak nuclear forces. But at the moment the universe started, during the Big Bang, these all forces were one force. And that's, some people call it supergravity, but also very famously it's called unified field theory. Einstein had a dream that we should have one equation in physics. There is one equation of force in physics that can define all the interactions and actions in the universe until the atoms. It can explain everything. But we are still haven't found it yet. Einstein even worked on that. It's something very interesting. So if you wanted to work on theoretical part of physics, in dense theoretical part, you can look into it. So collectively, when this all force were coming together as one single force, that's called unified field theory. So until 0 to 10 to the power 43 seconds, there were only one force in the universe, all of them collected together. From 10 to the power 43 seconds, the first decoupling takes place, where the gravity actually gets out and decoupled from the unified field theory. And the rest of the things were still together. That is called grand unification theory. That is strong nuclear, weak nuclear, electromagnetic together, and gravity separate. Then in 10 to the power minus 35 seconds, the grand unification theory ended because the strong nuclear force came out. So now there is only 2 forces are still stacking together in comparison to modern times, electromagnetic and weak nuclear forces. And we also see some appearance of some very elementary particles like quarks and leptons. Some people might know these terms, what is a quark, what is a lepton, but for some people it can be new. So what is it? It will just come in the next slide. You will understand what actually are made out of quarks and leptons. So when the age of the universe was from 10 to the power 35 to 10 to the power 30 minus 33 seconds, there was an inflation. That is, the size, the space of the universe has drastically increased by a factor of 10 to the power 30 to 40. So these terms, 10 to the power 30 to 40, is so big, it's probably not very easy to intuitively think about it, but it's a huge terms, because I mean 10 to the power 7 is 1 crore. So you can understand what 10 to the power 30 is. So the space of the universe was extremely expanded like that, which we call inflation. And the temperature of the universe, you can see, was also started to get down. It was infinite, but then it was 10 to the power 32 Kelvin. Just a reminder, Kelvin, you might all know, but still a reminder that how we measure temperature is mostly in Celsius or centigrade. Kelvin is a conversion. If you convert it, the 0 degree centigrade is 273 Kelvin. So it's just that conversion, but in that scale they are all equal, in almost equal. So in 10 to the power 32 Kelvin, then it slowly gets down to 10 to the power 27, 25, 27 to 10 to the power 15, and around 10 to the power 12 seconds, we see that all the 4 fundamental forces, gravity gone before, then strong nuclear force, then weak nuclear force, and the electromagnetic force was separated. And once they got separated, protons and neutrons started appearing from quarks. So these fundamental particles, I was talking on quarks. Quarks are basically the constituents of protons. We think that in common people think that, okay, we are made out of molecules, that then molecules are made out of atoms. Atoms are made out of protons and electrons, but protons are also not the end point. Protons are also made out of fundamental particles like quarks. So protons and neutrons, they started forming, And when the age of the universe was 10 to the power 7 second, then the protons and neutrons were in full production. So if you know the formula of hydrogen ion, it's basically one proton. So hydrogen, as a hydrogen particle, the hydrogen element started appearing at that time. So when protons and neutrons were started productions. And then the electrons from the leptons, they get a bit lower energy, and the electrons and positrons started appearing. And then when there are protons, there are electrons, positive, negative charge, they fall and they start forming atom. And which one? That is hydrogen. So around 10 to the power minus 4 second, the age of the universe, hydrogen started forming. Now, with much more time, like when the age of the universe were like few minutes, the nucleosynthesis era started, where with further reduction of temperature, the helium, deuterium, and some of these elements started forming. And then there were some few eras which I'll go beyond. And after few such eras, we get the recombination era, where till now, until these few seconds, few minutes, every matter and energy were almost in the same energy state. But after this recombination era, that is around 380,000 years, matter and radiation became separate. And matter had their own journey and radiation stayed wherever it was. So in that era, we get this CMB, which is cosmic microwave background. And the cosmic microwave background is the only direct observational epoch we have of the universe. There are some indirect ones, but the direct one we have till now is the cosmic microwave background. And after that, it took like 500 million years to form the first galaxies and few billion years to form the next stage of galaxies. And now we are 14 billion years after the expansion of the universe. So this is sort of the chronology of this universe. So if we put it in a plot of time, so at this point, universe has started from Big Bang. Then there was a cosmic inflation of space. Then particles come out, the ordinary matter, and also there is something called dark matter that also was there. They were forming a cosmic soup. It's all mixture of a lot of stuffs. And then in around 380,000 years ago, we get the recombination era, where all these things get decoupled. The four forces are now decoupled already. The matter and radiation are decoupled, and the matter started falling in together in gravity. So this dark matter, it interacts with gravitational force a lot. So this dark matter pulls the matters towards the gravities, towards their gravitational potentials, and they started forming the initial stars and then galaxies, and then the galactic evolution started. So it went on for billions of years, and eventually we are here today after 13.7, 13.8 billion years. So this, in the whole cosmic scale, is where what is the size of a galaxy? Not a galaxy, a size of a cluster of galaxies. So that cluster consists of so many galaxies. So from that one single point you see is probably our galaxy, Milky Way. And from that Milky Way, one single dust point is probably our whole solar system. And from that whole solar system, this pale blue dot, as Carl Sagan said, is basically Earth. So that's how small and tiny we are in comparison of universe scale. We are just even not a dust, actually. So I just want to, I just wrote this, I write this. Carl Sagan in Pale Blue Dot book actually wrote an amazing amazing paragraph on this, which I just want to say here. That is that, look again at that dot. So in this positive dot, that's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was lived out their lives, the aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinners in the history of a species lived on there, a mote of dust suspended in a sunbeam. So whatever we know of, if you think us as a very anthropocentric creature, that dust is all we are. And that's also the amazing part is from that dust, we are studying our universe, the origin of the universe and everything, how it's began. So I know this might make you sound insignificant, but this can also give you the confidence and also a scape of exploration of how much we need to know. So let's talk a bit on the technical part now, that how we observe this universe, how we got to know these stuffs. And the answer is the telescopes. But there are various types of telescopes. There are ground-based telescopes, space telescopes, and also high altitude or airborne telescopes, which can be further divided into different types. So if I go on into the first type, which is the space telescope. So the space telescope are also divided into three parts. So the Earth orbiting space telescopes, there are different orbits of Earth where the telescopes are actually placed. And then, I mean, there are medium orbit, lower Earth orbit, higher orbit. Also, there are geosynchronous orbit, geostationary orbit. And but the satellites, the telescope we use to study the space, they are mostly in the HEO, MEO, LEO band of the orbits, and they are used to observe the space in UV, optical, infrared, X-ray, and also gamma. So what we see in the space is just the visible light, the optical, but we don't see the UV, IR, X-ray, gamma in our naked eye. So why? The reason is that Earth's atmosphere has two windows basically. So only from the whatever lights coming from Earth, they are either optical, that is 400 to 800 nanometers, or radio waves, 1 millimeter to 10 millimeter. The rest are all mostly absorbed or totally absorbed. UV and infrared are mostly absorbed, some part comes to Earth, and X-ray, gamma rays are totally absorbed. So to observe the sky properly, we need to go above Earth's atmosphere and place the telescope so that we can get all kinds of electromagnetic radiation and study what is the source of this electromagnetic radiation. So these are some kind of very popular telescopes like Hubble, which you probably have heard of, then Chandra, XMM Newton, New Star, Fermi, and all. Astrosat and Exposat, these are Indian built X-ray telescope made by ISRO. Exposat was launched very recently, a few months ago, and Astrosat is here for a few decades, not few decades, 1 decade, a bit more than 1 decade probably. So these are the kind of Earth rotating orbits. Now there are also other Lagrangian point telescopes that we use, because we are in a binary star, not a binary star, we're in a binary system where there is a star and there is a moon, and also Earth. There's Earth and the sun is mostly there, and there is moon. So it's a 3D model, but a restricted 3D model. So in that, you will have multiple gravitational stability points, which are in technical terms called Lagrangian point telescope, Lagrangian point. And the telescopes we put in the Lagrangian point are called Lagrangian point telescopes. So generally we put the telescopes either in L1 point or L2 point, even though there are 5 of them. So for example, in L1 point, there are telescopes like SOHO, AESS, Discover, and even Aditya was also the Indian telescope which was put there. So the L1 point is between sun and Earth. So it studies the sun very well, the sun's atmosphere, the wind. And also the telescopes like Discover, it also studies Earth properly, the whole atmosphere, the whole surrounding of Earth. So it does both of the stuffs. The telescopes in L2 point, they generally are observed generally are interested to observe the whole universe, or at least better the solar system or our Milky Way. So this telescope like JWST, which is very popular these days, anyone interested in astronomy probably heard this name, James Webb Telescope or JWST. There's also Euclid, Gaia, Planck and all. So these are in the L2 points, which is farther away in this part, which you can see in the diagram. So why we use L2 points and L1 points? Because these points are extremely stable in the thermal environment, which we don't get when we are sending Earth orbital telescopes. There is no sun, moon, Earth blocking when you are watching the sky. So it's outside, especially the L2 is outside that zone. There is much low background radiation and smooth spacecraft orientation. So when you are watching the sky, sometimes you have to orient the panels into the space where you want to observe the sky. So that is also quite smoother in space compared to in the other kinds of telescopes. And in L1, we mostly see the sun, because we can see sun without any eclipse. So that's a good advantage. And also it's better to monitor the solar winds and the atmosphere if we are closer to the sun without any eclipse. So these are the Lagrange telescope points we use. Sorry, this is a mistake. This should not be Lagrange telescope point. Anyways, the next I will talk about is high altitude telescopes. So high altitude telescopes are not the telescopes that is in the orbit or in the space, but it is in between. So it is within like 10 to 40 kilometers of our surface. So as I said before, that only optical and radio waves can reach us, and the rest are get absorbed. But still we get a bit of infrared rays, very small amount of bit of infrared rays. So to study those infrared rays, generally these balloon telescopes or airborne telescopes are used. So we this infrared or this radio waves. So these are very famous infrared satellites or radio satellites. There is boomerang, this blast, spider, superbeat, and they are just a balloon. So it's a huge balloon, and you put the instrument and you leave it. You just leave it as it is, and it will go up in space and it will take the data. It's just like that. Now, why? Because as it go up, the 99% of the atmosphere is gone. So you can lift a large amount of instrument and have lower noise, basically atmospheric noise. But the problem is, if the weather is unstable, the balloon is gone. Also, if there is wind and rain, everything is very much problematic. Also, the flight duration is limited. So you send the balloon and it will stay for a few days and it will come back. So you have to plan your observations on the basis of that. So this is cost effective, but will not give you excellent study. But still, it's a very useful thing to do if you are in a limited budget. And another one is airborne telescope, which looks a bit funny actually. It's basically a telescope inside a plane. It flies at an altitude of 12 to 14 kilometers. There are a few telescopes like that. Sophia is the latest one. It has a similar kind of advantage like the balloon ones, but the problem is here there are lots of whenever you get on a plane, you see lots of air turbulence. So if there is an air turbulence, your data is gone. And also there are residual temperatures and also other parts. So there are quite a bit of problem that you can handle. You have to handle if you use this kind of telescope. But also in a limited budget scenario, this can be very useful. If there are extremely bright infrared observations or infrared sources in sky, probably this telescope can be very useful with low budget. So this is also one of the high altitude type telescopes we use. And apart from that, we mostly use ground-based telescopes. Now, the telescopes generally has been popularized, very much popularized in Europe by Galileo, but it was not actually by Galileo. People before Galileo also invented telescopes, and it was in there for even few hundred years before. But the modern telescopes we use, they are much more sophisticated with better resolution. So ground-based telescopes, we generally divide into two parts. One is low energy telescopes and high energy telescopes. Where the low energy telescopes is optical, near infrared and radio. You can measure these things. Optical, it's whatever optical light is coming. It's just that. Near infrared, because far infrared or mid infrareds are all absorbed in the atmosphere, and radio is what we actually get. So the advantage of this kind of telescope is that it's easy maintenance. It's close to you. If there is a problem, you can just go there and do your work things with that. It's also low cost in comparison to space telescopes, but it has limitations like atmospheric turbulence. For example, it happens a lot that you want to observe a specific part of the sky at specific time, and then there was rain. So everything is ruined. So this, you might need to get used to that also. So generally, these kind of telescopes are very much in the high altitude, especially if there is less atmospheric disturbance, also low clouds and humidity. This kind of telescopes was good. This is me. This is a 3-meter DOT telescope, the Devastal Optical Telescope in AESS, Nainital. This is the largest optical telescope of India. And this is me very much pixelated standing here. Anyways, and this is the largest, one of the largest optical telescope of the world, which is 10.4 meters in Canaries Island of Spain. So these are the kind of ground-based low energy telescopes. But human beings are smart. So what they have done is, even though we cannot absorb certain things directly from certain wavelengths, but we can observe them indirectly. How? So they use these high energy telescopes. How is it that they observe the gamma rays of the high energy? Gamma ray is like in giga electron volt, or it's higher than that. So how they observe it? That this telescope, what it does, it does indirect detection of how these gamma rays affect the atmosphere. So it's like when you see a car moving very fast, it creates a shock, a strong wind. That wind is basically shock. So that shock hits you, right? So it's just the same, but in electromagnetic field. So if it's a very high energy gamma rays, it ionizes the atmosphere instantly, and that instance is like 1 picosecond to 1 nanosecond. So it's not visible to our eyes. But we can make instruments that can measure these flashes, and these flashes are called Cherenkov flashes, basically Cherenkov radiation. So if we can measure these flashes at a very certain period of time, then we are indirectly detecting the source of the gamma rays. So we are not detecting directly gamma rays, but indirectly detecting gamma rays. So that's how many of these recent years, the HASE, MAGIC, and then CTA is a very popular one, which will be coming in few years. So they observe the sky gamma rays. So you don't need a lot of money to send telescope into space for gamma rays. You can also observe it, but indirectly. But there are some limitations. That is, any ground-based telescope limitation is atmospheric turbulence. And also there are weathers, and there are absorption blocks of UV X-rays. So if you want to do a multi-wavelength study, how of the gamma ray source, like if there is gamma ray, also X-ray and optical ray, you cannot do simultaneously. You have to just be satisfied with the gamma rays. So this is the MAGIC telescope. This is the ground-based high-energy telescopes. That's how we study. So I will try to be a bit quick. I think I talked a lot, but I will just go on to some stories. And so how the cosmic microwave background was discovered, as I was talking about telescopes. So in 1964, these two very cool dudes, Arno Penzias and Robert Wilson, they detected mysterious persistent microwaves, and it was creating a hiss. So the thing is that whenever they are moving their radio telescope all over the space, they are getting a consistent noise, which they used to call hiss, and which they couldn't understand in a particular wavelength. So they initially thought they had some problem with the electronics. They calibrated it. They also checked the pigeons, because when they first time went there, they actually saw that some pigeons pooped over the radio telescope. So these things can happen. And they thought that, okay, so pigeon poop is a dielectric material that can give this constant noise. So they cleaned everything was done, but then they again check and they found that there is this constant hiss coming from all around the sky. And the temperature when they calculate of this radio wave, it is around 3 Kelvin, which is like minus 270 degrees centigrade. So at the same time, there are some Princeton physicists like Robert Dicke, Jim Peebles, and David Wilkinson were searching for some leftovers of cosmic radiation that came from Big Bang. So these two people eventually got in touch together, and they are like, okay, so whatever you are watching is the leftover of the cosmic radiation. So this is the direct evidence of Big Bang, and this is called cosmic microwave background radiation. Why microwave? Because the wavelength was in microwave. And eventually for this discovery, Penzias and Wilson got the Nobel Prize in 1978. Sadly, this guy, Andrew McKellar, also discovered it years, like 2 decades ago, this similar kind of source, because he was doing some other stuffs, and he also noticed in kind of he was studying interstellar medium, and then he saw that the similar kind of radio waves are coming from all directions of the sky. He presented it to the people, but they rejected his results. And sadly, he died around 1960, so he didn't even get the recognition or the Nobel Prize. But this was the first discovery of cosmic microwave background. That is the evidence of Big Bang. So what they found was something like this, where it was like a hum. It feels like a smooth coloring of it's a smooth color, and the temperature was consistent at 3 Kelvin. Then there have been much more updated radio telescopes which have calculated that the temperature is not exactly 3 Kelvin, it is like 2.7 Kelvin. And the Planck is one of the latest space telescopes which tried to calculate what are the fluctuations and some other properties, and they found that this, you see, it might not look very homogeneous, but this is because these fluctuations are of the order of 10 to the power minus 6. So it's very tiny fluctuations, and the temperature is around 10 to the is around 2 to the 2.7 Kelvin. So keep in mind that the temperature of the universe is 2.7 Kelvin, which is around minus 270 degree Celsius. That's how cold the universe is at now. And they found that this spectra is basically fitting a perfect black body. So black body spectra is basically, most of you know, but it's a body which in thermal equilibria can emit and also absorb whatever radiation they can. And this spectra, it shows a black body with a temperature of 2.7. This is from Kobe observation. So this is the strongest evidence of Big Bang that we have till now. So just from that, I will just go on to the life of stars. So we get to know what happened with the Big Bang and how the universe was formed and whatever we get to know from the direct evidences. There are much more to talk about, but that would become a coursework. So let's just touch a bit what is the life of a star. So life of a star is a bit like us. We born, we live our work, and we die. There are certain number of things we do in between, but in global scale, that's what we do. So, but the difference is stars die, but then it born again. There is no direct evidence of our re-emergence. There is no such thing as afterlife or all has been detected yet. But for stars, we have found. So how that happens is the stars formed because as if you remember that there are giant molecules of gas that was formed during the beginning of in the beginning era after CMB. Now those gases with hydrogen and helium, only hydrogen and helium, keep in mind, there were no other kind of elements. All the higher elements you see, this is very interesting. At least I got it very interested when I first heard it, that all the higher elements above helium, that starts from lithium to carbon, nitrogen, oxygen, iron, copper, gold, silver, everything was made inside galaxies and stars. So everything that you see close to in your vicinity, close to you, including you, they are all made by stars. I mean, universe only made hydrogen and helium, that's all. And the rest of the things were made inside a star's core. So how they are made, we will talk on that. So the giant clouds actually began collapsing because of heavy gravity. And as they collapse, the density increases. As the density increases, the temperature increases. And eventually they fall inward. I mean, these things have very critical calculations, but I'm just summarizing it. So they form something called protostar, where the gas starts falling inward, it accretes, and it creates, it's like few thousand Kelvin temperature, forming a protostar disk. And as the core temperature rises, the fusion reaction, nuclear fusion reaction starts, because the gravity is so heavy, as if it collapses in a small dense region inside the star. And we see that this hydrogen fusion starts, and it actually gives a pressure balance to the young stars. How the pressure balance happens is, this is how you see in the simulation how the stars is colliding, how the gas are colliding, and the stars starts forming. Basically, you see this red points. So after being born, star directly go to adult life. No, not like us. So in the early adult life, what happens is the hydrogen in the core of the stars, the hydrogen starts burning. So hydrogen is the fuel. So that, as long as hydrogen is there, the star is in the adult life, at least in the early adult life. So hydrogen goes through a fusion reaction, and it emits helium and energy, and the hydrogen fuel eventually gets diminished, right? So what happens is this, as the energy comes out, this energy comes out as a radiation, and that gives a pressure to the gas, to the gaseous state. So the star wants to expand, but there is also strong gravity that also tries to pull it together. So there is a huge tug of war between gravity and radiation, and that gives the stability of the stellar life. So when you see your sun, it's stable because the huge amount of radiation wants to come out, giving a radiation pressure, and then gravity is countering, giving a gravitational pressure. Is almost there. No one is winning the battle, basically. So it's in a stalemate situation, and they are in a state, or in a stable state. This stable state is called hydrostatic equilibrium, where the outward pressure and the inward pressure is equal. And they stay like this for billions of years until the hydrogen fuel gets finished. So once that happens, we'll go to the next slide for that. But by that time, as energy moves outward in the radiation, we can see. Sorry? Great. Noises are everywhere, which you have to deal, so you should not get frustrated. In these cases, for the energy transport, as the energy moves outward by radiation, it goes to the radiative zone and the convective zone, which you see here. And from there, the light comes as a visible light. The radiation comes as a visible light within 400 to 800 nanometers towards our eye. So just for the information, it's also, I didn't write it in the slide, it takes like 50,000 to 1 lakh years for the radiation, for the light to come from the center of the core of the sun to the surface. It takes 50,000 to 1 lakh years. And then from surface of the sun to earth, it takes like 8 minutes, 8.45 minutes. So the light you see is actually has originated almost 100,000 years ago. So probably at that time, the human civilization was not that. Homo sapiens was not in these conditions. So the light, when you go to the sun to get some vitamin D, that vitamin D is coming, not coming, that vitamin D photons are coming from like 1 lakh years ago, probably. So anyways, after this, the middle life, what happens is when the fuel gets run out, but there are helium also. So the helium gets accumulated in the core, and the core actually starts slowly contract, because till now it was a very equal battle between radiation pressure and gravitational pressure. But as the radiation pressure gets weakened, the fuel is running out, the gravitation starts to initiate. So it slowly contracts, and as it contracts, it hits the hydrogen in the shells. So initially the hydrogen in the core was burning. Then the hydrogen shell burning starts with the collapse of the gravitational pressure. And as the hydrogen core burning starts, the star initially collapses a bit, and then it starts expanding slowly. And this fusion reaction in the hydrogen core makes it expand like I think 10 or 50 times the size of what it is, or 100 times the size, and it becomes a red giant. So if Sun becomes a red giant, it would probably gobble up Mercury and Venus and Earth, probably, or at least Earth will be totally vaporized when our Sun will become a red giant. But don't worry, it will take like 4.5 billion years. I don't think human species will be alive the way we are dealing our planet these days. So what happens is that as we reach to that transformation of the red giant, this red giant is, by the name, it becomes red in color. So the temperature is a bit low, and but the gravity inside gets so strong. There is a gravitational collapse that helium also starts burning into millions and millions of Kelvin, and helium becomes carbon and oxygen, and then oxygen and carbon starts burning, and it becomes iron. So everything that you see that I was talking about actually formed inside a star's core. So I think you can predict that the things you see next to you was not made by Sun. There was a star before. There was probably a stellar system before our solar system that has made all these things, and we are using that gift. So but this is the process of the middle life of stars. So what happens after that is that that is the old age and the end of the star, when even the helium, after that the iron and everything burns out. There is no more radiation pressure to push out the immense amount of gravitational force. Gravity collapses, and it collapses and collapses and collapses into such way that it the sun-like stars basically shed away the outer layer, and it leaves a very a very small size carbon oxygen core. But the core is so dense that it becomes something called white dwarf. It cannot fall further, because till now the radiation pressure was countering gravity, but it becomes so small in stellar scale that now the electron degeneracy pressure, that is, you know, that electron has their own pressure. So electron has their own nature, and that gives the pressure, because electron in some definite orbits, in some definite energies, should remain same, so that the natural laws are consistent. But if the gravity is so strong, electron degeneracy actually stops this pressure until certain point. If it can stop it, it becomes a white dwarf. It becomes like that. At the center there is core, and at the surface there are high energy electrons who stopping gravity from further collapse. But if there are stars which is heavier than Sun, the collapse go further, and it overcomes the electron degeneracy, and the carbon, basically the carbon-rich core actually further collapses into protons and electrons, creating a very ultra-dense core. And the outer layer, while collapsing, it explodes into a supernova, which you can see in this simulation. So only the core remains, and the rest of the stuff goes out as a supernova. So this supernova you see here is the Crab Nebula, and that's how it was formed, hypothetically. So if it is a more massive star, the core further collapses from white dwarf to neutron star. But if the star is much bigger, and instead of red giant, the star becomes a super giant, red super giant, then the star follows something that is called Chandrasekhar limit, which I'll talk about in the next slide. It collapses further and it eventually becomes a black hole. So all the pressure of gravity overwhelms all kind of atomic forces basically, and it eventually becomes so dense that even the escape velocity it becomes higher than the speed of light. So even light cannot come out from that kind of object. So this object is called black hole. It's black because because light cannot come out. It's whole because it feels like everything is falling inside but nothing is coming out. So Chandrasekhar actually Subramanian Chandrasekhar, a legendary astrophysicist. He was also the nephew of C.V. Raman, who also won a Nobel Prize for Raman effect. So Chandrasekhar has calculated this maximum limit of white dwarf star, and he found that if the value of the star is 1.4 times the mass of sun at adult life, then the electron collapse degeneracy would prevent, and it will be a white dwarf. If the star is less than that, then also the white dwarf will stay and there might be some supernova. But if the mass is more than 1.4, that is between 1.4 to 3, then it will become a neutron star and it will be an explosion like that, which is called supernova. And if the mass is more than 3 times the mass of the sun, then the star becomes a black hole. And for this discovery, he got a Nobel Prize. But the reason I put Arthur Eddington's name here also, that when he actually proposed this theory, Arthur Eddington rejected it. He was a legendary physicist. He was a legendary professor at that time. But he totally rejected his theory that he thought there can never be something called neutron star or black holes. Because electron degeneracy is how quantum mechanics work. You cannot just say that something much more stronger is breaking electron degeneracy and you are making something like a neutron star or a black hole. It sounded very absurd. So for years he has questioned, and he has extremely conflicted with him in different conferences. And Chandrasekhar was extremely depressed for that because one is confidence and second is also the harassment. So after a certain point, he actually left this part of astrophysics and he started working on some other part. But years later, so this discovery was in 1940s and 50s. In 1980s, he actually got recognized, Chandrasekhar, and he got the Nobel Prize. So if you are right on something, stick to it. So this is, in short, the life of star, where there is a stellar nebula, where is actually the molecular clouds, which either can become a massive star or an average star, depends on the constituent of the nebula. And then it can become a red giant or a super red giant, then some explosion, supernova. If it's a supernova, it will become a neutron star or a black hole, or if it's a planetary nebula, it will become a white dwarf. And then the rest of the gas mass will again go inwards in the stellar nebula, and again the star formation cycle takes place. So when you see higher elements near you, they are formed with a life cycle of star that was before our solar system existed. So I will end this talk with this cosmic calendar, which was very much sorry, I think I took a bit more time, but like 1 hour, but I'll just end this talk in this with the cosmic calendar, where we fit all our universe history in 12 months. So this I read first time in Carl Sagan, and then I saw Neil Tyson's show, which I guess many of you have saw it, but just for the greater audience, I'm just explaining that if our universe was born on 0000 AM, 1st January, and if today is 31st December, 12 PM, then how the universe actually, how in that scale, what has happened throughout the universe. So the Big Bang happened and the stars formed in the first month. But then the galaxies started forming at the end of January. Then from February, the galaxies are developing, the galaxies are getting bigger. So initially they are dwarf galaxies, then they are getting bigger galaxies probably. And after that, there are more star formation, and eventually at certain point our Milky Way, galaxies are also colliding with each other, they are breaking apart, so these things can happen, and eventually there are more new galaxies, and we have Milky Way at the month of May. So after Milky Way was formed, I think the next few months goes with the actions of Milky Way, and then in the month of September, then in the month of September, we see the first solar system. So universe was born in January. Until September, we see solar system. There is no sign of human yet, but there is sign of some life from the month of October. There are some very unicellular lives, the cells, and which has been throughout October, November, and then from December, the multicellular life has formed. And then if we break down more the December, the first couple of weeks of December, there are almost nothing. And then we actually get the first trace of fossils. So first land animals started appearing on 14 or 15 December. Then some land animals with bones and shells. Then the vertebrates appeared on 18 December. Then the other land animals, the fish, all the stuffs we started seeing. First flower came on 28 December. Dinosaurs were around 29 December. Dinosaurs got extinct on 30 December. They stayed for 1 day in this calendar. Then came the apes, so our ancestors. After that, on 31st December, the humans and chimpanzees actually split. So the human beings evolved. Our species started appearing from 31st December, 8 p.m., considering this scale. Our human beings started walking from 9:25 p.m. Our human beings started having bigger brains and using sharp tools from 10:30 p.m. The modern human evolved at 11:52 p.m., just 8 minutes before midnight. And human migration started 11:56 to 59, just 2 to 3 minutes before midnight. And then in the last second, whatever we know of is how have human societies have evolved, from cave paintings to Indus Valley civilization, Mesopotamia, Egyptian civilizations. Then the Jesus Christ was at the last 5 seconds, and then in last final 1 second, we see all the developments. So the scientific revolution was below 0.8 seconds. The first industrial revolution was 0.6 seconds. The first telescope was probably around 0.9, 0.8 seconds. And then we had world wars, Cold War, and eventually we are at 0. So every human activity, scientific activity especially, that studies the universe took place at the last second. So whatever we get to know, that's how smart we are. That I think we should acknowledge, that with such small cosmic time scale, we have evolved, and we are almost trying to find out whatever is happening in the universe, and we are closing the gap quite fast in an exponential way. So on that note, I just give you this romantic point of view of the cosmic calendar, and I will finish my talk. Thank you.
Thank you so much, Da. With this, we come to the question answer session. So anyone with a question may feel free to ask. First the online, then we come to the offline. Any online audience who would wish to ask any question may ask.
Just a reminder, this is something that one of my very close professors told me, that there are no bad questions, but there are bad answers. So you should not be scared to ask questions. I should be scared to give the correct answers if I'm wrong. So you can ask me anything you want, no problem. And if I'm very convincing, it's fine.
You can also post the question in the chat section. So That is also we can do. I think no question from online, so
Good evening, sir. Good evening, sir.
Sure, no problem, sir. It's fine. Okay.
Okay. Sir, my question is, you told about the expansion of universe. Sir, I was studying a book on Sean Carroll. There I found that the energy is not conserved by the covariant divergence of the energy momentum tensor equal to 0. Then, sir, where does that energy go?
I mean, I think if you, I haven't got through that book, but I think they might have explained something. Either during the stage of inflation, there have been some activities, but it's not very clear. I mean, my frank answer is I don't know. The conservation of energy at the large scale, we say, yes, energy is conserved. But if we see the thermal history of the universe, there are lots of discrepancies, lots of asymmetries. We don't have any direct evidence. We have lots of models, particle models, standard models. So it's still very theoretical. So I cannot give you a better answer. But probably that book can. So you can continue reading it.
Okay, sir. Sir, my second question is, sir, we say that gravity is a manifestation of the space-time. Then why do we consider it as a part of force?
Not like part of force. I mean, in more technical term, we say gravity is an interaction. So as an interaction is something that when multiple systems are somehow communicating with each other. So on that part, you can say that this is gravity is just an interaction, same as strong nuclear interactions, weak nuclear interaction, electromagnetic interactions. The term force is, you can see, still in used in many parts because of the historical reasons. Because before Einstein, everyone used to believe that gravity is what Newtonian explanation was, and that is force. So it is just a plain inverse square law. So they consider it as that. But it is basically the bending of space-time metric, and it's just interactions. So in more technical term, you can think like that.
Sir, my last question is, sir, when you told about the chronology of from the Big Bang to today, sir, what time does the QGP form, quark-gluon plasma?
Well, I can't remember at the top of my head, but I think it was in my slide. Just I want to check a bit. So yeah, the quark-gluon plasma was when the grand unification theory was just ending, and the quarks started coming out. The nuclear forces were started separating. At that time is the epoch of the quark-gluon plasma. So that will be around 10 to the power minus 35 seconds. Or 30 seconds left.
It is around like during the inflation period.
Later, the inflation actually, that is before. So just after that, the sort of the inflation started, and then the quarks actually was much more in the universe, and then they formed the quark soup. So the beginning was actually around the inflation. You're right. It's the end of the grand unification theory and beginning of inflation.
Okay, sir. Thank you so much, sir. Good evening, sir. My question is, what challenges do researchers face when trying to detect particles or signals from extremely far away regions of the universe?
Yeah, I mean, it's a part of it is mentioned in the talk where we need space telescopes. So for a better clarity, so that the atmosphere does not absorb or reflect a part of the informations that coming from space. The rest is most of the studies comes from studying light. So whatever wavelength it is coming, whether it's radio or whether it's gamma, it's X-rays, optical. So if that source is heavily obscured, heavily covered by a bunch of gas or some galaxies, then we can indirectly try to find what is happening inside. For example, if there is a very high energetic source and there is a huge cloud that's covering it along our line of sight, then we will see excitations, emission lines, or even some absorption lines. So studying those spectra, the emission spectra, absorption spectra, continuum spectra, we can like predict the nature of the energetic source or the nature of the source in general. So there are some direct processes, but also some indirect processes. So it's hard, but we try to find it in some way, either studying spectra or studying like emission spectra or absorption spectra. Apart from that, if there are also sources that has problems on that even that electromagnetic spectra cannot detect very accurately, then we very recently started studying gravitational waves. So gravitational waves can also, so this is not studying light, but studying gravity. So if, for example, but in a very extreme situation, so if two black hole merges, the space-time actually creates a ripple and it comes as a wave. So you can study the wave of the gravity, and then we can try to understand what is happening inside very much in the short time scale of the source. So our, the thing is, our roots are limited, but from the limited roots, we can always try to find out as optimal information as we can. So that's what we try to do. Just like you've seen in the how we see the gamma rays from the ground-based telescopes. We don't see it directly, but we see them indirectly. So this is how we try to do. So I just gave you a few examples. I guess I answered your question.
Thank you, sir. Sir, this is Satya again, sir.
Okay.
Sir, I want to ask about, sir, I want to pursue my MS in theoretical physics and in mathematical physics, more inclined to that. Sir, I am currently searching for some research internships or any kind of internship in that side. Sir, if you have any contact or any knowledge on that in your university or your knowledge.
I mean, mine is a research institute, but I think you can look onto the websites of research institute and universities, whether they publish any, or it's like that. There are some websites like Job Register, I think you know, and Job Register. There's Job Register like that. And also there are some more, I think you can find it, but they give you this list of calls for either internship, for junior scientists, or also for PhDs. So you can look into that, or you can go to the university pages if you have in mind some 20-25 universities. Go to that, or even if you specifically like to work with some people, you like specific works of some researchers, you read some papers of those researchers, you can directly email them also. I think their email is available in the university website, the official email. You can email them with your CV and with your interest.
Sir, the problem will be because, sir, I am from engineering background, so with that perspective, they might not take me seriously.
No, that's not. There, I have seen also in my institute there are quite a lot of people from engineering background and doing serious astrophysics. So also theoretical. It's not very uncommon. It can probably be a bit uncommon in a certain structure, but I would say that in US, in Europe, and also in many other parts, Australia, you would see a lot of people coming from different background and doing something absolutely different.
Okay, sir. Thank you, sir.
Hello, sir. I have a very simple question to ask. So, due to, sir, all this light noise which we are currently facing. Sir, how you still find it, how you still observe the universe in, at least in visible spectrum? Because for us as a hobby, if we try to pursue it, it's very difficult to, observe this all planets and stars in, at least in the city environment. So, sir,
Yeah.
how do, in modern, sir, modern telescopy, or how you find it, any technique, modern technique that you use in these observations?
Yeah, it's just what you also, I mean, the answer is in your question actually. In cities, you can never do that. You have to go to places where there is no light pollution. You have to go to above. I mean, if you consider amateur astronomy, I would say if you have a good telescope and you want to just observe the sky, some like moon, the craters, the nebula, all these things, the planets, Jupiter, Saturn, and all these things, you have to go to villages and with a bit high altitude, and where the sky is a bit clearer and the humidity is a bit low. There, I think you can observe. Otherwise, it's with light pollution, it's not very possible. That's why all the observatories that I was talking about, those observatories are built at a very high altitude, or in a place that has almost no light pollution. So if you ever get to chance to visit in some of these places, you will see that there are no lights at all. Like, it's very strictly prohibited to turn on even your mobile phone. It's like that, and that's why we also send our satellite to space, because there are no humans in space yet. So there are no disturbances of light. So.
Thank you, sir. My next question would be, sir, about, sir, if we are just following this science field habitually because of our hobbies, so what books should we read, sir?
It's a very good question. Actually, that is also a bit my mistake. I should have put some books here. So if you are interested in more like on the popular science things, then you can read Carl Sagan or some initial books of Michio Kaku. The late books I will not recommend because it's very fictional, not very scientific. But the initial books, what he used to write, you can also read The Brief History of Time of Stephen Hawking. And also Stephen Hawking have many other books which you can read. I mean, that's quite simpler, I would say. It's not very rigorous mathematics. And also Neil Tyson's has some books which is popular science. But if you want to do a bit serious science, I would say you can read Ryden, R-Y-D-E-N. Ryden has a very good cosmology book. There is a people called Maus, M-A-O-Z. He has a nice astrophysics book. There is Carol Ostley, has a very nice astrophysics book. These are very textbook things. So you can go through that. I would say start from anyone. If you just do a small Google search, whatever books comes, depending on what you want, to read some popular science stuffs or serious equation-driven stuffs. Whatever book comes, start with that, and then you will see in the journey it goes.
Thank you, sir. Thank you.
Good evening, Dada. So I have two questions. The first being, does a black hole leads or ends to a white hole?
There is no. First of all, it can. I mean, there are a lot of speculative hypotheses, I would say, because generally people also say a lot of things that this is a theory, but unless it has proven evidence, these are not theories. These are just hypotheses. Now, from Einstein's general theory of relativity, you can derive. It's some people say. I mean, I haven't thoroughly worked on general relativity equations, so I don't know exactly. I haven't done it firsthand. But people who works on relativity says that they can theoretically, by calculations, they can predict that there can be things like white hole. But
what's the end of a black hole? Like it is said that whatever, if there is a beginning, there should be an end. So like no one knows the end of a black hole. So
I mean, no one knows yet. The thing is that a black hole, you can think of it is a space-time curvature. Are you aware of space-time curvatures?
Yes, little.
Okay, it's like you can think of it's a fabric of cloth, and you put a ball, so the fabric of cloth gets deformed. So it's like the space-time is like that. So any heavy object, like heavy means like not like a person or a table. Heavy means
The
Earth,
gravity.
stars, galaxies. They bend space a lot. So for black hole, it bends the space so much that in the space-time metric, it almost becomes like a hole. So if something goes there, just directly goes inside. Now, once this thing goes inside, I mean, we don't know what happens inside. So my answer from that extrapolation will be it stays inside. It gets destroyed and it stays inside. The black hole grows. That's a very popular thing actually, because black hole is not like it stays at the same shape. Because anything falls into the black holes or the conservation of mass and energy. So anything falls into the black hole obviously grows. But it stays inside. At what form, where it exactly goes, the answer should be it's inside the black hole. But how, we don't know.
It's a mystery. And can a wormhole help us to achieve time travel, or can it be related to black hole?
Well, if you are a fan of Christopher Nolan's movie, then there is obviously the movie is made very well in this part actually. So it's not time travel; it's more like space-time travel. So with a wormhole, you can travel from one space to another space just in an instant. So how far the distance is? So yeah, you can do that, but the time travel will not be exactly like that, because when we measure time, we measure on the basis of some reference frame. So it will not be exactly like that. So for example, if a person from point A to point B reaches there, and then you use a wormhole and reach to the point B immediately, then on the basis of that, you have reached in sort of future. But if you are both in a present event, it's not time travel, it's more like space travel. But saying that, I would say wormhole is also a very theoretical thing. It's also not, we don't have any direct evidence of any wormholes yet, even though this is also one of the results of general relativity, which says that wormholes are possible to exist, and it does not affect the universe nature and laws.
Okay, thank you.
Okay, so I have this question. It just came to my mind randomly, so it might not be properly framed. So the thing is that you said that the Big Bang is the starting of the universe, right? So all the matter, energy came from that single bang. So my question is there is another aspect to it, that is the space, right? So I guess space also began from the Big Bang, if I'm wrong, or if I got. So if space also began from the Big Bang, so the point where the Big Bang actually happened, so it should exist somewhere, right? Like somewhere in space. So where was it exactly? I mean, it's a very hypothetical idea. So if you can address that.
We don't know. I mean, the thing is that you can think Big Bang, but there are certain things or certain questions where we can say that this question might be invalid from our perspective of science. Because if you want to know what happened before Big Bang, or what was the exact space and time of Big Bang, that is not a correct question. It's good that you ask, but it's not a correct question. Why? Because the whole concept of space and time originated after Big Bang. So whatever we understand as space and time in our science, that's originated after that. So anything before, it cannot explain. Now I can give you a very simple example. For example, if I tell you to go to North Pole, you will where will you go? You will probably leave this institute, and then you will start walking towards north, and eventually you will reach Delhi, then Kashmir, and then eventually China, Russia, and you will reach the Arctics. So if I tell you to go further north, you will follow the North Pole's direction, and eventually you will go to North Pole. And if you stand exactly at the point of North Pole, and if I tell you to go further north, then that's an invalid question. So wherever you go from there is the South Pole. So space-time is that. I mean, Big Bang is that. If you go farther back and back and back, and you go to the time where everything started, and then I tell you to go farther back, that's invalid. So wherever you go back. It's the similar kind of topology. So you can think on that. But yeah, from the perspective of science that we do, we don't know this thing. And also, there are many theories of what was there, not theories again, hypothesis. What was there before Big Bang? What will happen when the universe will end? There are like big bounce theory that the universe will expand at certain point and then again go back, and again a Big Bang will happen and again expand. So these are all hypotheses. We don't know these things. So these are more game of the theoretical physicists. We are much more in the observational and whatever things we see, we are much more into that. But it's a nice question.
Thank you.
I cannot hear you. I think I'm muted.
As we come to the end of this enriching session, it's my privilege to deliver the vote of thanks on behalf of the IEEE AESS KIIT SBC. First and foremost, I extend our deepest gratitude to our distinguished speaker, Dr. Dhrubojyoti Sengupta, for gracing us with the presence and sharing his invaluable insights through today's thought-provoking talk. I'd also like to thank our advisor and professors for guiding us throughout and helping us make this event possible today. A special word of thanks to all the XCOM members whose dedication and teamwork helped in executing this event successfully. I would also especially thank all the participants for joining and learning with us today. A special mention goes to the IEEE Student Branch Chapter for being there with us. Thank you very much.
Thank you, everyone, and thank you for patiently listening to my talk.
Thank you so much, Anand. So with this, we end our meeting. Thank you all for joining.